Basically, in complex integration, consists of open line integrals and contour integrals. Contour integrals can be evaluated by three methods. The simplest being the application of Cauchy's integral theorem. Next, the Cauchy's integral formula. 3. The Cauchy's residue theorem. These are the possible ways in which we can evaluate complex integrals. Well, we will not spend much time in complex line integrals of the open type because most of the important theories lie in this one. These open line integrals are very similar to what we do in vector line integrals. So, we will focus directly on the contour integrals. Now, all of you know what a contour integral is. A contour integral typically looks like this: integral f of z dz over a contour C. So, if you take the complex plane, then this closed curve taken in the anti-clockwise direction becomes the contour. Now, when you are integrating over this contour, then those theorems can be very useful to us. Now, let us see what happens in the first case, that is the Cauchy's integral theorem. In the Cauchy's integral theorem, the output of integral f of z dz over C will be 0 provided a very strong condition is satisfied. That condition is when f of z is analytic. If f of z is analytic. What do you mean by an analytic function? A function is said to be analytic when it has got no singularities in the given region. A singularity is as value of z which will make the function undefined. For example, if you take f of z is equal to 1 by z plus 1, we say it has got a singularity at z is equal to minus 1. So, if there exist no singularities inside the contour, then the Cauchy's integral theorem says integral f of z dz will always be 0. But if you change the contour and if the function has singularities within that contour, then the output cannot be 0. So, there are two cases. When the singularities are inside the contour, then you get non-zero outputs, and those can be estimated using the Cauchy's integral formula or the Cauchy's residue theorem. But if there are no singularities of the function inside the contour, then the output can be safely assumed to be 0. So, I will show you two problems where we have a function which is analytic that has got no singularities in the indicated region, therefore, the answers will be 0. Let us look at those examples. Question number 10. What is the output of integral z square dz where C is the square with vertices plus or minus 1 plus or minus I? Now, you know there are 4 points here, namely minus 1 1, minus 1 minus 1, 1 1, and 1 minus 1. So you can plot this in the complex plane. These are the 4 points. Integration always anti-clockwise. So let us see what is the nature of this function with respect to this contour. So if you look at f of z is equal to z squared, this has no singularities. It has no singularities means it is defined and differentiable at all points in the complex plane. So therefore it has got no singularities even with respect to this square. Therefore, by Cauchy's integral theorem, integral over c z square dz has to be 0. In fact, every algebraic type of function will have no singularities at all, whatever be the contour. The singularities arise once you have denominators involving functions of z. So the correct option for this problem is A. So you can see that no integration has been performed, but only the function has been tested. If the function is analytic, then you can be rest assured that the output of this integral will be 0. Let's look at the next question. Question number 11. What is the output of integral phi z to the power of 4 minus z cube plus 2 dz around the curve consisting of the parabola y is equal to x squared from 0 0 to 1 1 and then along y square is equal to x from 1 1 to 0 0. Strictly speaking, we need not waste any time on this problem because once again this is a polynomial function and therefore there are no singularities for this function, whatever be the region. Some students end up drawing diagrams and labeling them and all that, forgetting that this function has got no singularities. So we'll coolly say that f of z is equal to phi z to the power of 4 minus z cube plus 2 has no singularities. Therefore, the integration of this function will be 0 as indicated by option A. However, I would like to explain here that what can be the situation in some cases. Let's look at a problem like integral sine 2z by z minus 1 dz. Let us take two cases. Case 1, c is mod z minus 2 is equal to half. Now when you look at this function with respect to that contour, you know this is representing a circle with center at 2 comma 0 and radius half unit. Okay, so this will be what? 2 plus half, that is 5 by 2 comma 0, and this point will be what? 2 minus half, 3 by 2 comma 0. So these are the diametrically end points. But if you look at this one, z is equal to 1 is a singularity, because it is at this point this function is not defined. But you can see that z is equal to 1 is not inside the contour. Z is equal to 1 is somewhere here. Therefore, the value of this integral will be 0 by the Cauchy's integral theorem. But if I expand this circle by making the radius is equal to some 3 or 4, then z is equal to 1 will go into the contour. Then the output of this integral is no more 0, and that has to be evaluated using a theorem other than the Cauchy's integral theorem. That is where you get the Cauchy's integral formula or the Cauchy's residue theorem, about which we will discuss shortly. So, if the function has no singularities inside the integrated region, the output of the integral is 0. That is the essence of the Cauchy's integral theorem. Let us now start Cauchy's integral formula. Let us first look at this formula. In fact, there are two formulas to be remembered. The statement is if f of z is equal to u plus iv is some complex function and C is a closed contour, integral over C f of z by z minus a dz is equal to 2 pi I times f of a if A is inside the contour. So, this is the simple statement of the Cauchy's integral formula. So, you can see that z is equal to A is a singularity of this function. So, if the singularity lies inside the contour, then the value of this integral is 2 pi I times, be very careful, it is f of a, that means the numerator evaluated at this singularity, not the whole function. An extension of this is integral over C f of z by z minus a to the power of k plus 1. So, this will be 2 pi I by k factorial kth derivative of the function evaluated at that point, again if A is inside the contour. Specifically for k is equal to 0, you get back this formula. If you got whole square here, k becomes 1 and you will get 2 pi I by 1 factorial into f dash a and so on and so forth. So, Cauchy's integral formulas are two formulas, one having a singularity with power 1 of order 1 and a singularity of order k plus 1. Suppose the singularity does not belong to the contour, then you know already by Cauchy's integral theorem that the output has to be 0. So, it is all very simple, either the answer is 0 or an answer like this, depending upon whether the singularity is inside, not inside or within the contour. So, let us take an exercise to understand this. Question number 12. What is the output of the integral z square minus z plus 1 by z minus 1 dz, where C is a contour mod z is equal to half? Okay, first let us draw this. You must know that mod z is equal to r always represents circles with center at the origin and radius r. So, we have a circle here. Centered at the origin and of radius half. Now, let us look at this problem. The numerator can be seen as z squared minus z plus 1. Now, this whole function has z is equal to 1 as a singularity, because at z is equal to 1 this function is undefined. Now you check whether this singularity is within this contour or not. You can clearly see z is equal to 1 may lie somewhere there. So it is outside the contour. Therefore, by Cauchy's integral theorem, integral of the given function will be 0. The correct option, as you can see, is A. So in subsequent problems, whenever you find the singularities within the contour, then the Cauchy's integral formulas become applicable. So let's go to the next question. Question number 13. What is the output of the contour integral e power 2z by z minus 1 into z minus 2 dz, where c is mod z is equal to 3? How to plan this problem? First, draw the contour. It's a circle of radius 3 units with the corner points minus 3, 0, 3, 0, 0, minus 3 and 0, 3. So let us say f of z is e power 2z. When you look at the denominator, z is equal to 1 and z is equal to 2 are both singularities. And if you observe, z is equal to 1 as well as z is equal to 2 are within the contour. So it is expected that we get a non-zero result unless there is some sort of cancellation. Anyway, this is a problem where we can apply the Cauchy's integral formula. How do you do it? Both the singularities are inside the contour. So what you do is, you keep aside e power 2z and you take 1 by z minus 1 into z minus 2 for partial fractions. So a is equal to 1 by 1 minus 2, which is minus 1, b is 1 by 2 minus 1, which is 1. Therefore, this function can be written as e power 2z into minus 1 by z minus 1 plus 1 by z minus 2, which is the same as e power 2z by z minus 2 minus e power 2z by z minus 1. So this function has been expressed like this. And if you remember Cauchy's integral formula, for this part, the singularity is z is equal to 2, which lies inside the contour. So the answer to the problem can be worked out. Assuming this is f of z, the answer will be 2 pi I times f of 2, because this is that, minus 2 pi I times, again for this part z is equal to 1 is the singularity which lies inside the contour. So therefore you will get 2 pi I times f of 1. So this is 2 pi I into, if f of z is e power 2z, f of 2 will be e power 4 minus f of 1 will be e square. So we can search for the answer in the given options and we will find this is present as option number D. So this is a very good example where we have both the singularities inside the contour, therefore partial fractions have to be used, but I hope students are aware that partial fractions is only for rational functions. So you cannot include e power 2z into the partial fractions plan. Therefore, you separate out e power 2z, take 1 by z minus 1, z minus 2 partial fractions, rebuild the function in terms of fractions and apply the Cauchy's integral formula. So, this is how we can solve. In the problems that are going to come, you may find one singularity inside and the other is not inside. So, I will tell you how to handle those situations. Let's go to the next question. Question number 14. What is the output of the contour integral sin pi z squared plus cos pi z squared by z minus 1 into z minus 2 dz, where c is mod z is equal to 3. This is very similar to the last problem. And once again, the singularities are 1 and 2. This is 3 comma 0. So, again you take partial fractions of this function, you will get 1 by z minus 2 minus 1 by z minus 1. So, therefore, the problem is now sin pi z squared plus cos pi z squared into 1 by z minus 2 minus 1 by z minus 1 dz. So, if you take this numerator as f of z, the output can be arrived using the formula 2 pi I f of 2 minus 2 pi I f of 1. The minus is because of this minus. So, 2 pi I into f of 2 is sine, put z is equal to 2, sine 4 pi plus cos 4 pi minus of f of 1 sin pi plus cos pi. Now, you know sin n pi is always 0. So, this will be 0, this will be 0. So, you will have 2 pi I into, you already know cos n pi is minus 1 to the power of n. So, this will be 1 minus of minus 1. So, this will be 4 pi I. And you will find that the correct option for this problem is A. So, this is another application of the Cauchy's integral formula, where both the singularities are inside, therefore, partial fractions becomes necessary. Let us go to the next question. Question number 15. What is the output of the contour integral z plus 4 by z square plus 2z plus 5, where C is the circle mod z plus 1 minus I is equal to 2. This looks a little bit more difficult than the previous examples, because we have to identify the singularities carefully and then even to draw that contour. Of course, there is no confusion, this is a circle, but center not at the origin. So, you can write this as mod z minus of minus 1 plus I is equal to 2. Then you can easily identify the center is at minus 1 comma 1. And the radius is 2. So, we have a circle now with center in the second quadrant minus 1 comma 1 and whose radius is 2 units. This may be slightly difficult to draw, but there is a systematic way to approach. So you create two diameters with this as a center, measure 2 units. So this is one end, this is the other end. This will be 1, 1. This will be -3, 1. And in the vertical direction, you come down here. You are at -1, -1, and you are at -1, 3. So you now draw a circle like that. So this is the contour whose complex equation is this. Now our analysis should take us to whether the singularities of this function lie within the contour or not. So let's look at this one. Z square plus 2z plus 5 can be written as z minus alpha into z minus beta, where alpha beta have to be found. They are the zeros of this polynomial. So alpha and beta will be -2 plus or minus square root of 4 minus 20 by 2. So this is -2 plus or minus 4i by 2. So -1 plus or minus 2i. So we can say alpha is -1 plus 2i, beta is -1 minus 2i. Now you'll have to go to the contour and see whether these singularities lie inside the contour or not. So this written simply is -1, 2. This is -1, -2. Let's look at -1, 2. -1, 2 is somewhere here. So we have located alpha inside the contour. What about -1, -2? It is below this point. So beta is equal to -1, -2 is outside the contour. So what does this mean? It means if you can write z plus 4 by z minus alpha into z minus beta, alpha is inside the contour but beta is outside the contour. Therefore, this z minus beta can be promoted to the numerator because it's not a singular point. So to this you can apply the Cauchy's integral formula. So if you take this as f of z, then the answer should be 2 pi I f of alpha, because alpha is a singularity. So this is nothing but 2 pi I into f of alpha, means replacing the numerator with alpha. This is alpha plus 4 by alpha minus beta. Now we can easily calculate this one because you have alpha and beta from here. So what is alpha minus beta? This will be this minus that. So you will get 4i. So this will be 2 pi I by 4i into alpha plus 4. Alpha is -1 plus 2i. To this you add 4. You will get 3 plus 2i. So if you cancel this, you will get pi by 2 into 3 plus 2i. You can find this as option C in the list. But look at the nice thing about this problem. It is a little bit complicated, of course not that very difficult if the planning is good. So first, fix the center and radius of the circle, draw it properly, and then you come and identify the singularities. You find the two singularities alpha and beta. Alpha can be located within the contour, beta outside the contour. So when you look at the calculations, you don't have to go for partial fractions. You can promote z minus beta to the numerator, call that f of z, and then apply the Cauchy's integral formula. So this is a very nice question, and problems around this can be expected at this level of examinations. Let's go to the next question. Question number 16. What is the value of f of I in the problem f of alpha is equal to integral over c 4z square plus z plus 5 by z minus alpha dz, and c is the ellipse x by 2 whole squared plus y by 3 whole squared is equal to 1. Now this is a problem where z is equal to alpha may be a singularity. Let's look at the ellipse first. The semi-major axis and this semi-minor axis can be seen. This is 2, 0. This is 0, 3. And you have an ellipse. Now let us assume alpha is a singularity, and if you call this numerator as some g of z, then the RHS is equal to 2 pi I times g of alpha. This is by the Cauchy's integral formula. So 2 pi I times g of alpha is equal to f of alpha. But we need f of I. So for alpha is equal to I, which you can see is nothing but 0, 1, which is here. You can say 2 pi I times g of I is equal to f of I. G of I will come from here. So 2 pi I times 4i squared plus I plus 5 is equal to f of I. This is I square minus 1. 5 minus 4 becomes 1, and f of I will be nothing but 2 pi I into 1 plus I. If you take I inside, you will have I minus 1. This and this are both correct, but when you look at the options, I think this we can find as option B. So this is a simple application of the Cauchy's integral formula, but remember there is a doubt when you start whether alpha is within the contour or not till he declares alpha is equal to I, and that can be located within the ellipse. Therefore, we can apply. Okay, let's go to the next question. Question number 17. What is the output of the integral cos z by z minus pi I whole squared, where c is mod z is equal to 5? First, let us draw the contour. It's a circle centered at the origin. Of radius 5 units. This function has a singularity at z is equal to pi I. You take the numerator as f of z. Now, how do you understand z is equal to pi I? Pi I means along the vertical direction. Presence of I indicates that the singularity is on the imaginary axis. Of what magnitude? Pi. So, this is 3.14 approximately. Pi is approximately 3.14. So, the singularity is along the y direction at a distance of 3.14 units from the origin. So, definitely it is below 5. Therefore, you will find that pi I is located there. Pi I is approximately 3.14 I. That means along the imaginary axis. So, it is now confirmed that the singularity is inside the contour. Therefore, to this we can apply the Cauchy's integral formula. By Cauchy's integral formula for derivatives, the output will be 2 pi I by 1 factorial first derivative at the singularity at pi I. Remember, the rule is integral over c f of z by z minus alpha to the power of k plus 1 is 2 pi I by k factorial kth derivative of the numerator function at the singularity alpha. So, here our numerator is cos z, and you must differentiate it once, evaluate it at the singularity. So, now let us see what is f dash z from here. F dash z is minus sin z. So, f dash pi I is equal to minus sin pi I. But you know that there is a very important relation which says sin I theta is equal to I sin hyperbolic theta. Accordingly, you will get minus I sin hyperbolic pi. So, when you substitute this into the function here, you will get 2 pi I into minus I sin hyperbolic pi. Minus I square is 1, so the output is 2 pi sin hyperbolic pi. And you will see that this answer is found as option C. So, you must also know these relations in order to conclude a problem. Otherwise, you will find that you are doing something wrong. Let's go to the next question. Question number 18. What is the output of the contour integral e power z dz by z into 1 minus z whole cube, where c is mod z is equal to half? So, this is a circle of radius half. Let us take the numerator as f of z. You have two singularities, z is equal to 0, z is equal to 1. But you will find z is equal to 0 is inside the contour, but z is equal to 1 is outside the contour. So, even though z is equal to 1 is a singularity, it does not belong to the contour. So, you can promote this to the numerator. So you can bunch this into the numerator, e power z by 1 minus z whole cube by z dz. So this will be the new f of z. We can write for convenience z minus 0. So the output of this is 2 pi I f of 0, where f is this numerator. So this is 2 pi I into e power 0 into 1 minus 0 whole cube, which ends up as 2 pi I, showing A as the correct option. So this is again a simple problem. Why these problems are being taken is some students may land up doing partial fractions, which is really not required because z is equal to 1 is not inside the contour. So the idea is very simple. Those singularities which are within the contour should be retained in the denominator, others should be promoted to the numerator, so that you can minimize the denominator part so that the calculations become easy. Let's go to the 19th question. Question number 19. What is the output of integral e power 3 z dz by z minus log 2 to the power of 4, where c is a square with vertices plus or minus 1 plus or minus I? So these are the corner points of the square. Let us take this numerator as f of z. We will check whether the singularity is alpha is equal to log 2 is inside the contour. First of all, this is a real number and the approximate value of log 2 is 0.69. Don't mistake it as 0.3 because that is for the common logarithm base 10. Natural logarithm log 2 is approximately 0.69. Now this is a 1 unit. So 0.69 is definitely inside the contour. So this is the location of alpha is equal to log 2. So it's very much inside the contour, and you can find that this 4 can be visualized as k plus 1. So when k plus 1 is equal to 4, k is equal to 3, and the output by Cauchy's integral formula for derivatives is 2 pi I by 3 factorial f triple dash alpha, where alpha is log 2. So we need to differentiate this function f of z is e power 3z 3 times. So f dash z is 3 e power 3z, f double dash alpha is 9 e power 3z, f triple dash alpha is 27 e power 3z. So when you apply it here, you will get 2 pi I by 6 into 27 e power 3 alpha. Alpha is nothing but log 2. So this will be nothing but 2 3s, 3 9s, 9 pi I e power 3 log 2, e power k log a is a power k. So this is nothing but 2 cube. So 72 pi I is the output. Nothing very great about this problem, but there may be some students who cannot handle logarithmic quantities as singularities. It is for them. Otherwise, it's a straightforward problem, and the indicated answer can be seen in B. Question number 20. What is the output of contour integral cos 2 pi z by 2z minus 1 into z minus 3 dz, where C is mod z is equal to 1? This is a unit circle centered at the origin. There is a small adjustment required here, because in the ideal form we require z minus alpha type of situation. So you can extract these two outside and write half cos 2 pi z by z minus half into z minus 3. You can find that z is equal to half and 3 are singularities, of which z is equal to half can be found on the real axis, but z is equal to 3 is outside the contour. Therefore, this can be promoted to the numerator. So we can write this as half cos 2 pi z by z minus 3 divided by z minus half. So we will treat this as a function. F of z is equal to cos 2 pi z by 2 into z minus 3. The singularity is alpha is equal to half, and the answer should be 2 pi I f of alpha, where alpha is half. So 2 pi I f of half, 2 pi I cos 2 pi alpha, that becomes cos pi by 2 into half minus 3 minus 5 by 2. So these two can be cancelled. Cos pi is minus 1. Therefore, minus of minus becomes plus, and you will have 2 pi I by 5. And you will find that option B is correct for this problem. So these are some of the examples which can be used for practicing around the Cauchy's integral formula and the Cauchy's integral formula for derivatives. However, before concluding this session, I would like to tell you that if you know the Cauchy's residue theorem, then you can perhaps get the same results a little bit faster using the calculus of residues. So we'll meet again for a session on the Cauchy's residue theorem and how these integrals can be attempted by that route also.